Okay, good morning, and today we start is a continuation of clustering. Okay, yesterday we studied a bit about non-hierarchical clustering, where we do not need to find the value of k. Okay, we just jump into the water and we find fishes. We're looking for the clusters. Okay, we saw the dendrogram. Now moving ahead in that sequence. So if we apply a monotone transformation to the two kind of distances, if you remember, the linkage, the single linkage and the complete linkage. Okay, so the single linkage, when we consider the points of two clusters very close to each other, the minimum distance between them. And the complete linkage was when we consider the furthest distance between the two clusters. Okay, so in these two cases, these linkages, if we apply a monotonic transformation to it, they are invariant. By invariant we mean if at a certain point we have two clusters, okay, at a certain distance, and we have, let's suppose, three clusters. Okay, this was the example from yesterday from the natural water of Italy. Okay, we wanted to know similarity between these. So in the previous slide, we were looking at a monotonic transformation to the two kind of distances, to the linear linkage, single linkage, and complete linkage. They are invariant of this transformation, meaning that in this case, how many clusters we have here? 1, 2, 3, 4, and 5. Okay. If we apply any kind of linear transformation to it, the number of clusters will still remain the same. There will be 5. Okay. But just the amount of their transformation we applied, this distances will change. So if it's increasing transformation, maybe the first cluster we make here, the second cluster maybe we make it here. Okay, so just the distances are changing, the partitions, the clusters will remain the same. That's why when we choose these two kind of distances, the single linkage and complete linkage, they are invariant of transformation. In the second case, when we have the average linkage, if you remember, average linkage was a compromise between the single and the complete linkage. Okay, we used to take the two distances and take the average of them. So this kind of distance is not invariant. Why? Suppose if you first take the two distances of between the two clusters, distance of one cluster and another cluster, sum them, average them, and after that you apply the monotonic transformation, you will get one distance here, let's say 3.5 here, just an example. In the other case, if you first apply the transformation to each distances, so first you apply transformation to the first cluster distance, then to the second cluster distance, and then sum them and take the mean. So in this case, maybe you will receive 4. So you see the distances are different and they are inside the clusters. Okay, so then you will have a different shape completely inside the cluster. Okay, so for these reasons they are invariant. Okay. Now, to which clusters we can say they are well structured, they are well partitioned. If you remember from yesterday, we said two clusters are well clustered if they have a clear separation between them. We remember this, right? Otherwise, we have confusion, and if we have confusion, then we don't have explanation for those confusing or mixing around. Sometimes it can take some really weird stuff, weird structure. Maybe one cluster is like this, the other is like this, okay? So a well-structured partition there should be a clear-cut distance between them, okay? And by definition, it should be like this. The minimum distance, looking here, the minimum distance between these two clusters. Let me try to do it here. So, say we have one cluster here, okay, and then we have another cluster here, okay. Let's say this is the centroid, the mean point of the cluster. And if you want to know any maximum, any furthest point inside this cluster, for example, between these two, this is the maximum distance, okay, from the centroid to any point. So distance from here to here is minimum than this. Distance from here to here is minimum than this. Distance from here to here is minimum. So this is the maximum one inside a single cluster. Okay, so this maximum distance should be less than the distance from here to any other point across another cluster. Okay, so this D max should be less than this D minimum. It's confusing. Meaning here, if between, in a single cluster, if this distance is the maximum, okay, so this should be less than 1, the distance between these two. If this case is true, then so this cluster will having more similar units together, and between these two clusters there will be a much further distance from each other. So between these two, between this cluster and this cluster, there is less similarity. And here is the maximum similarity between the points. Okay? Are we good? So simply it's meaning that within a single cluster, you should have a homogeneous units. Homogeneous meaning there should be more similarity in here. And the other cases, there should be differences between the two clusters. Okay? So looking for another criteria for the minimal well-structured partition is when the number of clusters are small, so you have less number of clusters, okay? So in the case of single linkage, complete linkage, and average linkage, as you are merging your clusters, so you are going from n clusters, we remember from yesterday, from n clusters to n minus 1, n minus 2. So in the beginning, we had in the example 5 clusters, then we had 4 clusters, then 3, 2, 1. So as we are going up, there must be a certain point at which we can guess, okay, these number of clusters are enough for us. They make more sense to us. We don't want it to go more than this. Okay? So in practice, this could be the dendrogram can give us a hint about this. Okay, and what's that hint? The hint is if you're making a jump, if you're making a new cluster, in this case, for example, the last one, if between this cluster and cluster number 1, if you're making this jump, if you see the distance is huge, so the jump is big, okay? From one cluster to another cluster, the jump is big, the distance is big. What it means? It means that if the distance is big, this means that those two clusters are more indifferent from each other. There is more difference. So when you sense some kind of shift like this in your dendrogram, you say, okay, I cut here. Okay, and for me, just these clusters are enough. Okay, so meaning below this distance, the clusters are much more similar to each other. Okay, and above this cutoff point, the clusters are different from each other. Okay, so this is kind of criteria for us, just looking at the dendrogram and we decide. Okay, now from yesterday example, you were asking the question about the distance matrix. Okay, so in that example we had the distance matrix, it was already given to us. In the case of the water example, if you remember. So it was easy. We just, in that matrix, we just compared the distances and we started from the minimum distance. But if that distance matrix is not given to us and we start from scratch, we have just the raw data, okay? We have our point cloud, and from that point cloud now we have to make clusters. So how we go about this? We have to make some choices a priori before making our cluster decisions. Okay? And those are 3 choices we have to make before approaching the raw data set to make our clusters. And they are choice of the distance, which distance we wanted to use. Okay? The Euclidean distance, the Manhattan distance, or cosine similarity, or whatever. Okay? So this choice we have to make before. Then the next choice is, what's the linkage mode we wanted to use? Single linkage, complete, or multiple linkage? We remember from yesterday, if we choose any of these, the result will change. The dendrogram will change. We will have different number of clusters. So based on this linkage rule. So we have to make a choice for this. And then the final choice, how many clusters we want. Okay? So we should choose the number of k, number of clusters. So before approaching the problem, we should a priori decide these 3 things. Okay? And remember in MATLAB, if you don't say to it which distance to use, by default it uses the Euclidean distance. Okay? So the idea is this. You have a raw data set, you have your matrix, your point cloud. You choose the distance, which kind of distance you want to use between points, between clusters. So for example, the Euclidean distance. Then the next step is to calculate the distance matrix. Okay? And then for merging the clusters, one of these choices. And finally, we build the dendrogram. Okay? Yeah. As we said before, this was your question. from yesterday. How we choose the K. So if we have a big jump, as we said before, if we sense a big jump, we cut there and we say, okay, for us now K equal to 3. That's enough for us. Now an interesting scenario here. From our example yesterday, if you remember the first clusters if we had. Okay. So our first cluster is between 3 and 5. Okay. And the second cluster is between 3, 5 and 6. Correct? Then we have the third and the fourth. But a natural question comes into mind. Is one cluster is enough, or two clusters are enough? Because these two clusters are very close to each other. Are two enough? Are the choice to make three clusters enough? Or four? Or one? Okay? So this is a critical choice to make. Which one is the best? We don't know. Okay? So for this we need a kind of decision criteria. We need a way to say, okay, these clusters are enough for me. Okay? So even in MATLAB you can do it just with the function of dendrogram. What you say here, okay, for me distance at 0.26, the vertical distance at 0.26, if any clusters above this are making, don't consider them. So the clusters just below this distance are enough for me. And how you make this choice? Who knows? You just make a guess, look to the dendrogram and see. If you sense a big jump, okay, reduce this distance. If you're not sensing a big jump, okay, you say this is enough. Okay? And even this function gives you a kind of color so you can distinguish. So when you put the argument color threshold, so at this threshold, above this, the clusters will have a different color, and below this the clusters will have a different color. So this is a kind of mark, a threshold for you. Okay? Now just a simple example to know or to visualize how we can make two different groups, two separable groups completely from each other. So for this, let's have a random number. We generate some random numbers. The first group we make is, we call it x1, and it has n1 by p matrix. It has a normal distribution. So n1 is 10, p is 2. So 10 by 2 matrix for the first group of points. Then we generate the second group of points, which is having the same distribution, normal distribution. So before the normal distribution is centered at 0, now we make a shift, plus delta x, and delta dx is 5. So we kind of move every point by 5. Okay? And then we combine the matrix, and we want to know or to visualize how actually two separable, distinct groups look like. Yep.
How we can decide which one should be the centroid point of group cluster? For example, there we take the Dmax of B and we decide that is far away from the other cluster, and this one Dmax is the point where belongs to same cluster, but it's a maximum distance with the centroid. So how to decide which one should make the centroid?
It's a very difficult question. No, I'm kidding. We are going to this. Okay? We will find it in the next when we study k-means. Okay? In k-mean, then we have a technique, a random kind of technique where we look for the centroid, for the mean point. But here, in this example, there is no fixed value. Okay, there is no fixed value inside the clusters that you define. Okay, this distance or distance. For us here, distance has no meaning. Okay, distance just say to us how close, how far they are. And if we see here, for example, for the minimum distance we are talking. So, if the maximum distance is, let's say, 10, okay, then another distance is 7, then another is 6, 5, 4, okay. So this one is the minimum, and these are also minimum, but maybe the next point, this point is, for us, is 15, so which is too far, so I don't consider that. I roughly say, okay, if it's in this range, the algorithm decides, and we choose this. So you have a kind of bound here, okay? Okay, to visualize these 2 points, okay? Are you with me? We have created 2 groups, okay? One group is centered around the mean, the other we have a shift of dx, okay? So in MATLAB, how we do this? We initialize the random variable, we define our numbers, n1, 10, n2, 20, p is 2, and we generate random distribution of these points, okay? n1, which is 10, p, which is 2. So we have first group of points, okay? And then for the next, n2, which is 20, p is 2, okay? Then we combine the 2 groups and we just plot them. It looks like this. So the first group, which was around the center, is like this. The second is like this. And then we have also plotted this to show the row of each point. So first row, point number 1. Fourth row, second row, third row, okay? So just to visually see how they look like. What's the aim of this example? The aim here is just to show. We have one group here, we have another group here. There is a clear distinction between them, and the distance between them is like an ocean, okay? Any stupid algorithm can find these 2 groups, okay? So just to show, a well-structured cluster should look like this.
What is P is equal to? Is the group?
P is equal to?
P like what is the
Here,
no in the MATLAB.
here. We are taking this from here. So it's a 10 by 2 matrix. Okay, now, before going to this example, let me summarize the distances we saw yesterday and introduced a new distance, okay? So, for us, the single link was what? If between 2 distances, if between 2 clusters, we want to use single linkage, so the minimum distance between this group, the yellow color, so we have 3 groups here, yellow, red, blue, okay? And between all of them, the minimum distance between is red and yellow, between these 2 points. So this is single linkage. Okay, but the problem here is what? They kind of make like a long chain. Okay, so if we have points like these, okay, then we have some random, very weird shape. Okay, single linkage what does? Okay, between all of these, the minimum distance is this one. Then another minimum distance is this one. Then is this one. So it kind of making like a chain. Okay, and it does not consider the rest of the points. So which is one of the drawbacks here. For this reason, we move to the complete linkage. In the complete linkage, we consider the furthest distance between the two clusters. So red, yellow, blue. The furthest distance is this one. Okay? And what it does, it kind of okay. So if you are considering the closest distance, like between these 2 points, the closest distance, it's kind of like a circle. Okay, so from here to here, this distance. But in the case of complete linkage, we are talking about we are taking the furthest points. Okay, these points. Yeah. So it's made like a sphere. Okay? So that's why we can reach to more points. We can capture more patterns better. But here is a problem. You mentioned yesterday, the outlier. If you have an outlier here, this goes crazy. Okay? So then we move to the average linkage. In the average linkage, what we do? We take the average of all pair of distance, we divide them by the number. This is then something which is robust to outlier. Okay? So you take two distances, you average them, it confuses the game. So average, this is less affected by the outliers. Okay? And then we have another kind of distance which is centroids. So we take the centroid of one cluster, we estimate the centroid of another cluster. So between this is the centroid of this cluster, centroid of this cluster, and this is the distance now. Okay? So based on this we make the two clusters. Now we have the fifth type of cluster, which is called Ward's method. So in this method, which is more kind of similar to the complete linkage method, but here it does not consider the diameter of the sphere, but it considers the aggregate deviation from the centroid. Okay? So what we do here is, first we group two clusters. Okay? The red one and the yellow one. And we estimate their centroid. Okay? We group two clusters, we estimate their centroid. So this for us now is a new centroid. Okay? And then in the next step, we calculate the distance of each point to this new centroid. Okay? So for every point to this new centroid, we will have a different merge, we will have a different distance. And among all those pairs, we take the distance, the merge, which has the minimum distance. Okay? So it's kind of you're comparing before the merge and after the merge. Okay? So it's kind of within the cluster, it's looking to the deviation from the centroid point. So here is your centroid and it looks to this deviation, okay, and it merges just those points which are very close to the centroid based on their deviation from the centroid, okay. So here we have an example, and the example says to use Ward method, okay. Well, using the Ward method, we have to construct the dendrogram. We use the same matrix from the previous example, the same two groups, okay. And this time we use some threshold, a cutoff point for our clusters. And then we also display the frequency distribution, meaning that how many observations each cluster has, okay. So this is the Ward method. Finally, the formula here is this one. Just what will change when we are doing this inside MATLAB. So we have the method linkage, okay. Instead of putting single, complete or average linkage, we put the Ward, okay, and the rest is magic for us. So it takes this distance, okay. It's clear. So within the same cluster, we have this centroid, and we look for these deviations, okay, and we choose the minimum deviations from this centroid, and we call them as a cluster. Okay. Now to show it visually, as I said before, use the function linkage. Take your matrix, which is X. Method, we are using Ward. And the selection criteria for the other distance, we use the Euclidean distance, okay. And we also use the cutoff value, which is 7. So we need only 7 clusters, okay. And similarly, as we said before, this color threshold argument is for cutoff, to show you different colors at the cutoff level. And it turns out to be this one, okay. Looking here at the vertical distance, 5, 6, 7. So at 7 we have this cutoff, okay. We usually cut like this, okay. So the clusters above this cutoff, we are not interested. They are very dissimilar. Below, we are interested in them. They are very close to each other. So in this case, how many clusters we are considering? 3. Okay, the red one, the green, the blue. Why? Because we had a cutoff value of 7. If we had chosen any other value of cutoff, our interpretation results would have been different. Okay. And similarly, to know the frequency, like how many observations each cluster has, we use this function. We display what? The clusters and Ni. Ni is the index, okay? And this argument gives you how many observations you have. So, for example, cluster 1, it has 6 observations, which is like 20% of your complete data. Cluster 2 has 7 observations. Cluster 3 has 17 observations. And these all are below the cutoff value. Are we good? Anyone wants to count? Okay, and then we plot. Now there is another example in your book where you use this function, okay, SMP plot. You know SMP plot, right? Okay, but in this case we use our matrix and the ID. Okay, so the ID gives us how many points, which row, which cluster has which many points. Yeah. Okay, so we have two different observations here, y1 and y2. Okay, if you look, y1, this is before word method and this is after word method. Okay, so you see all of them have a very clear clusters. So the red one, the blue one, and the black one. Okay, as we saw also here. Okay, and similarly looking to here, the red one has a minimum distance, the blue is in the middle, and the black is shooted above. So the diagonal and off diagonal, if we are looking in that sense here. Okay, so we proved that. Okay. Looking into the dendrogram, we receive something like this: the red, the blue, and the green. Okay, and if we really plot them, we also see the same clusters here. So the red are making a very clear cluster, the blue are making a very clear cluster, and the blacks are making a very good cluster. And here we see their frequency. Okay, so this means our hierarchical method is working. Okay, now moving to, you want to have a break before going to, or are we good? After 10 minutes? Or now? Okay. So now moving to non-hierarchical clustering. So in hierarchical clustering, we don't know the value of key, k. But in this case now, we know the value of k a priori. Okay, so we choose the number of clusters we want to make. 3, 4, 5, 6. Okay, so we choose how many partitions we want. And k should be less than n. N are the number of units in your data, and k are groups. So you have 1000, n equal to 1000, k equal to 5. So 1000 is less than 5. Okay, it's kind of summary. So in hierarchical, we were making family of partitions. We started from n clusters, we move up into a single cluster. And in hierarchical clustering, we have to use the dendrogram, and based on the dendrogram, we get the idea where to cut off, how many clusters to keep, how many to throw away. Now the scenario here is different with the non-hierarchical. We have to know k in advance, how many partitions we want. So here we have to solve an optimization problem. If you remember hierarchical, we say it's exploratory algorithm. We are exploring something. We are exploring the structure. We are looking for some patterns inside the data. But here, a priori, we know how many clusters we want to make. Okay? So if we know we want to make 5 clusters, then for us it becomes like an optimization problem, an iterative problem. We want to look for patterns just to make 5 clusters, not more than those. And those should be the best groups, the best clusters, the best partitions. Okay? So when we are looking to it, to choose the value of k. It comes by practice, it comes with experimenting how many k's we want. But the key idea is two clusters should not overlap. There should be a clear separation between them, and within each cluster we should have a homogeneity. The points should be homogeneous. Yep. How to find the value of k? We have to look for it. We have to experiment. That's why it's called unsupervised learning. You remember? We had supervised and unsupervised learning. So what do you mean by unsupervised? What's unsupervised learning? Without labels. So the same case here, we don't know k. For us, k are labels. In terms of making clusters. Okay? So we have to discover it. But then there are various ways to know the k. Okay? Is it clear now? Okay. Here is answer to your question. Suppose we have n units and there are 20 and we want to make 4 clusters. Are you happy with 4? You want more? Okay. So how many possibilities we have here? Okay. Man, you can do it. We wait you find the best one for us in 45 billion. So it's very difficult, right? So we need to find an efficient algorithm where we don't have to look for 45 billion values of k. Yeah, many combinations here. So we should not check like 45 billion combinations in this case. Okay, just sum and pick the efficient one. Okay, so we have 20 data points. We choose k equal to 4. We have these possibilities. Now we need an algorithm to search intelligently what's the value of k. Okay, if you are doubting what I said, it's 45 billion. You can check it by yourself in MATLAB. Use this function. Okay. So what we need to have an efficient value of k, to have efficient clusters, we need an iterative method. And we start from an initial guess. Okay? And step by step, when we are going ahead with our optimization problem, we improve, and finally we stop somewhere where we converge. And we say, okay, this is our best value of k. Okay? So we start from somewhere, our initial guess. Okay? We assign points to each of the points in our data set. Then we start moving, shuffling the points to find cluster here. So maybe these points are going here, these points are going there. Okay? And then we do this process iteratively. Okay, it should be clear. Keeping in mind the objective. The objective should be very clear, which is inside each cluster we should have high internal cohesion. The cluster, each point inside the cluster should be very much similar. Okay? And between two clusters we should have separation. So this is our objective. Okay? To go into this objective, we do it after 5 minutes from the break. So you can see the bird from there? No? Yeah. Now? solo per capire quanti siamo. Quelli che non vengono li buttiamo fuori. Okay. We're back. Okay, so what we said before. Okay. So, how we can do help me? It's working, but no idea. Now, you're not hearing from here. Now? Okay.
Yeah.
We need to fix it here.
I think that it's directional shift. It needs to be kind of in front of your
Now you can hear me.
Yeah.
Perfect. Okay, so we said what are clusters? Unsupervised learning. And we have unsupervised clusters. So the key word here is unsupervised. Not unsupervised, but just un is the keyword for us. Okay? Here we need to find groups where we have more similarities. Okay? So one should have intelligence to divide things. We humans, we have intelligence to divide things into groups. Okay? So similarly, in computation, we are looking for an algorithm to divide stuff for us, to make cluster for us, to make groups. So, for example, for instance, if we have someone gave us a data, and they say to us, okay, we have data points like this and like this. On the x-axis we have horsepower. So it's a data set from cars. Okay? So the relationship here is horsepower and max speed. Okay? So this may be SUVs, this may be trucks, okay, and this
Sedan.
sorry?
Sedan.
Sedans.
Sports car.
Oh, okay. And then we have sports cars, okay? So we have these three groups here, you know? You know these three groups? Okay. So we can sense, okay, we have these three groups, and they have some kind of relation. If we have more horsepower, you have maximum speed. Maybe you have more horsepower, the manufacturer has made it some kind of, like the speed is less. So there is a trade-off between them. Okay. The first question is, are these clusters well separated?
Yes.
They're well separated. Kind of distance like an ocean. Okay. So we agree about this. The first rule is they should be well separated. The second rule is they are linearly independent. They are linearly separable, which does not mean like they have a kind of distance, which means that one should not have influence on the other. Okay? Meaning that inside a cluster there should be homogeneity. Should be very close to each other. Okay? Now the point here is, who told me to divide them into three groups? No one. I decided three groups. And there are three. Okay? But if I want to divide the same data into 4 clusters, or maybe to 5 clusters, probably the algorithm can divide those as well to 4 and 5. But then the problem comes that those results may be very difficult to interpret and maybe not meaningful for us. Okay? So these 3 are meaningful for us. Maybe the 4 and 5 clusters are not meaningful for us. We cannot interpret them. Okay? So then there are techniques to know these values of K. So we have 2 types of clustering. One is that they needs K. Okay, you should give them the value of K. Okay? A priori. But then there are another kind of clustering which do not need K. Okay? So in the second case, we do not need K. They are non-hierarchical clustering now. Okay? So, if this is the case, I don't have to specify to this algorithm divide the data set or make clusters of 3. I don't have to worry about that. Okay? The algorithm jumps into the pool and finds it by itself. Swims and look for those 3 clusters. I don't have to worry about them. Okay? So of course this is the best scenario for us. We just throw our data into the algorithm and the algorithm finds for us clusters. Okay? But the problem here is, in this case we have just 3 variables. It's very easy. We have just 3 clusters, 3 variables. Very easy to find these combinations and find the best key. But usually we are not working just with 3 or 2 variables. We have hundreds, we have 1,000 variables, okay? And then it becomes very, very complicated to find the best value of K in several hundreds variables. Okay? So here we have a problem now. For more than 3 or more than 100 variables, okay? So when we have a problem, we have a trick for this now to solve the problem. And the trick is to go for the K-mean algorithm. Are you getting me what I'm saying? We have a problem. What's the problem here? When we have more variables, then it becomes more complicated to do. Maybe you have to do several thousand iterations to find the best key, K, okay? So we move to the K-mean algorithm to solve this problem for us, okay? It was invented round about in 1970s. It's a very important topic in data science, statistics. That's why I shift here, so we should know it better. Okay? It was around 1970s, and after that we have several modifications, several versions of the K-mean algorithm. But the basic idea is the same. Okay? The basic idea is to look for find centroids. Okay? To find centroids. So, we have these points, 1, 2, 3 clusters. We have to look for centroid. Centroid is the mean of each group. Okay? So someone told me to find 3 clusters here. I have to go and look for 3 centroids, meaning 3 means in each group. Okay? So it's a simple idea to find centroid. Okay? Now the first step in K-mean is to place randomly K centroids. Okay? The first step, to start from somewhere. We don't know where is K. We don't know anything about the data. So we start by placing a random numbers, random Ks. Okay? For example, here we have, let's say the numbers are going to 100. Here we have 1000. Pick a number between 100 and 1000. It can be any. Okay? It can be outside of your data, it can be inside of your data, but just a starting point. We need to start from somewhere. We don't have any clue about the data. Okay? So to start from somewhere, okay, let's see. If I can redraw, no. I can redraw the same points. Okay, we start from somewhere. Let's say we started from here. How many groups we have? 3. We need 3 centroids. Okay? We started randomly. And we chose here. As we said before, it can be anywhere. It can be here, can be here, can be here. Okay? Then the second step is to assign each data point can you see from there? Assign each data point to its closest cluster. Okay? Assign each of these centroid to its closest cluster. Yes, that's the ultimate goal. We are going there. Okay. So the idea is to find the shortest distance of these centroids, but they are not centroids yet. They are just random points. They are random points, they are not centroids yet. Maybe in the next iteration, they become centroid, or maybe in the third iteration they become centroid. But for now, they are just random numbers, okay? Maybe can assign this one to this cluster. Maybe this is the minimum distance between them. Maybe this is the minimum distance between them. Maybe this is the minimum distance between them. And we are heading towards the mean. That's our objective. Okay? So we started with a random guess. Now if I stop here and I'm not moving, I'm doing nothing. Doesn't make sense. For those 3 random variables, I have to move. Okay? I have to move towards the centroid of those clusters. Okay? And now moving from here towards the centroid is the learning part. Okay?
So when we compute the distance, when we consider the distance from the k-means, from the points we have selected randomly, we're considering the distance of the centroid of the cluster over each point.
Yes,
Okay.
centroid.
So we're getting 3 distances.
Yes, we are getting 3 distances. Yeah. Okay? So that's the learning part. We should move. Okay? We know maybe we can reach there to the mean point in 100 iteration, in 1000 iteration. Depends on the data set, depends on the problem. So that's step number 2. Okay? In the third step, we need to update these centroids. Okay? Update these centroids. Move from here to here to here, or from here to here to here to here. Okay. Each time we update, we recalculate the distance, and we see if we are closer or we are far. Okay. So basically, we are doing two things here. We are calculating 2 different types of distances here. Inside here, we are calculating 2 different distances. Okay? And now we see what those are. Okay, so we have 2 scenarios. The first one is we have a centroid here, we have a random point here, not exactly centroid. And we have, let's say, 2 groups, 1, 2 groups. Okay, this is centroid 1, this is centroid 2. Okay. And this is distance of class adjustment. So this is distance of class adjustment. So we have 2 different classes, this one and this one. Okay. First, we want to establish our random C1 and C2 belongs to which cluster. So we have to calculate the distance from each point to here, to here, to here, and then to here, to here, to here. Similarly, here, 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 there, okay, and to here. So we have to calculate all those distances towards those random numbers, okay? Why we are doing this? Because we don't know those random variables belongs to each cluster. Okay?
So we stop when we find the distance, that is the minimized distance between the centroid and
some kind of very interesting thing happening here. When you visualize here, so the memberships changing here between the points, and it's very strange. Truck becomes SUV, SUV becomes sports, okay, at each iteration. Here, this becomes this becomes that, this becomes this becomes that. Okay? Because still we are not clear where is our original cluster. For that, yeah.
Like first iteration, we put random point for the centroid. We put randomly centroid from different places. And in the second step, we're shifting the centroid to different. That shift is calculated or it's also just random shift?
No, that shift we do this way.
This one
Yes,
shift
but
by
we calculate each time. So if we move here, we recalculate the distance. We move again, we recalculate the distance.
that shift is real. For example, you can move here. You can move also there.
Yeah, so this is completely random. That's why we say truck can become supercar, supercar can become SUV. Okay? Yep.
When will we stop?
That was my next point. When stop? When we converge. Okay? When we converge to these real points, to these original mean points of each cluster. And how would you know this? That we reached there? Then those distances around the mean point will not change. Or maybe they will be just oscillating here and here and here. And you are not noticing any big change there. When you say, okay, I stop. Okay. This for me is a good centroid. I stop here. I converge. Make sense? At the same time, we also calculate another kind of distance, which is this one. Okay, if I can replicate the same points. So C2, C1. Okay, and this is distance calculation for optics. This is distance calculation for updates. Okay, kind of error, not actually error. Okay, so now we are doing real stuff. Now within each class, we are looking for, are we here closer? Okay.
There might be a case, for example, if I try to train first time, it took random points somewhere randomly at any distance. So after one shift, it's not setting. After third, fourth, or sixth, we will achieve what we want. And when I try to train it again, I might get this actual position in 3 to 4 steps.
No.
Because the shift, the first shift is random.
Yeah.
And after that, that shift is not, we calculated the distance,
Yes.
but that shift is also random.
Yes.
You can put on different points on different points.
You're correct. So each time when you're starting with a random initialization. So maybe when you started with the first step, those points were here. And you did all your calculation, you end up somewhere. You're repeating the same problem, you're starting with another random initialization. Maybe it's here. You're reaching to the same point, then maybe there must be some differences to the final conclusion. The number of iterations, but it then depends on so many other factors as well. Arduino data is well separated. What's the structure of your data? There are so many factors, but you are right. If you change the initialization, you end up with something different, but not that much different. Okay, so it's very minor. Okay, so now here the point is I'm moving within each cluster, and at some point I decide, okay, this is my centroid. I stop here, I calculate the sum of the mean, the sum of the squares of the mean distances, and those distances should be the minimum one, as we were talking before. If they are the minimum one, we say, okay, I stop here. For me, the best I could do is this one, and this is the best centroid for me. I stop here. But if in the next step, if I recalculate those distances and I find another minimum distance respect to the other one, I say, no. Let's consider that one. Okay, because that one is minimum. So we do like this, and finally we have our best centroid. The best centroid where the sum of the distance, the square of the sum of the distance is the minimum. Okay? Which is the case like this. This is the centroid. These are the near points. This one, and this one. So those points reached here. Okay? These points are very close. Here, here, and here. And if these distances are minimum, we have a good centroid. Okay? Now we use here a term called error, but it's not actually error. Okay? We say as long as we are moving, suppose we are moving from here to this point, but let's say we are here. So still we are far from the mean point. So for us this is a kind of error. Okay? We should minimize this distance. Okay? And another point to consider, just from computational point of view, we should do this path as a straight line. We should go to the center straight. Okay, not to kind of some contour. Okay? Because it matters, computation cost. Okay? So we should find the minimum distance to go to the center. Okay? And again here, all these things we are doing with the help of similarity, dissimilarity, proximity, closeness, how close we are to the group. We are doing it with distance. Okay? Anywhere we consider just distance. So we trust distance. Okay? If everyone is cooking with water and you start cooking with oil, you will end up killing yourself with high cholesterol. So, distance, we trust distance. Everyone is cooking with water, we cook with water. Okay? So, these three steps. So, we have to find this distance. Okay? And this distance is, for example, we have, this is our point. We have this point, distance between this. So, we have point xi, point xj. To find the distance from here to here and from here to here. And that distance is dij, the distance between 2 points is equal to the square root of xi1 minus xj1 whole square plus xi2 xj2 whole square, and we go. Okay? So this is like the xi minus xj, the L2 norm, okay? The good old Euclidean distance, which we all love. So here we use this distance, okay? Now, if this distance is small, okay, you are close to me, we make a cluster. If this distance is big, you are not close to me, you cannot make cluster, okay? The minimum the distance here, minimum this distance, this, we are having a homogeneous cluster. Is it clear? Okay? So the objective here is to minimize this distance. Okay? So which would be the summation, so which is basically the error. We said this, should be more close to the distance. Okay? So this should be xi minus xj, Euclidean distance. Okay, the L2 now from k equals 1 to n, this distance should be minimum. So the sum of the squares towards the distance, we should minimize this distance. Okay? Now, just few points and then we are finished. Yep. Where? Sorry? Repeat, please. No, we predefine. Those we predefine. So KD algorithm, one of the drawbacks. That's what we were looking for. One of the things is you should first a priori say I need these terms and this amount of clusters. So k is equal to 3, k is equal to 4, k is equal to 5. Okay? So the core idea here in k-mean is to update, to make these iterations, okay? And this small algorithm can do unbelievable things, okay? You will see them in the science. Where we should stop, that's the problem, okay? We all have this question, where we should stop. So we start from some initialization, okay? We initialize somewhere, then we calculate the distances, we calculate these distances, and then these distances, right? We start from some initialization, we calculate these distances, then we go to this objective function to look how minimum this distance is, and then we update. But how long we will go like this? Initialize, calculate distance, establish the objective function, update. We are going, okay? So when should one stop? Okay? So there are 3 criteria to stop. The first one is you can stop after some iterations decided by yourself. Okay? Take your experiment, tell the algorithm stop after 100 iterations. It will stop, look at the output, is good, accept it, no, run another optimization problem and assign more clusters. Increase, decrease the number of k. This is the first rule. The second is when those centroids does not change anymore. When these centroids are fixed, they are not changing anymore. We stop here. Okay? And similarly, if no or few of the points are none of these points around the center, the data points are not changing anymore. Okay? So here might be you will have the situation like the points are oscillating, okay, and then you cannot decide to stop or not to stop. Okay? kind of scenario when you say the glass is half empty or the glass is half full. It's the same thing. It's oscillating. They have the probability like 0.5 in one cluster, 0.5 in another cluster. The good thing would be that an algorithm could tell us, okay, this new point is 0.9% here and 1 here. So meaning that probability 9, 0.9%, no, with probability of 0.9, it belongs to this cluster. And with 0.01 probability, it belongs to this cluster. If an algorithm existed like this, it would have solved our problem. But no. Here, K algorithm is binary. It says to 0 or 1, so you cannot decide. Okay? So then, what we do? Flip a coin. Decide. Okay? It's the same. If the glass is full or empty. Half full or half empty. Okay? Okay, we're good. We're on time. Final 3 points. Problems with K-mean algorithm. The first problem is we need to know K a priori. So we should a priori define the number of Ks. The amount of clusters. It's very sensitive to outliers. If you have outlier, again this goes crazy. Yeah.
Sir, aren't there any other tests to use with the reaction to just know the optimal K?
Are there any other techniques? You mean?
These tests.
Like, because the problem here is we don't know nothing about the data, and we have to start somewhere.
Yes.
Okay.
After training, we can have some ideas.
Yes, but yeah, then you can have something. Yeah, we have to start, but that's after when you discovered something.
Yeah, but
At the beginning,
always
we
starts
don't know
with-
nothing. At the beginning, we have no idea. Yes, people are using different techniques in machine learning. Yeah, I know that. But still, you don't know. Some people use like they consider 3 points randomly here, 3 here, 3 here, taking the average of these 3, taking the average of these 3, taking the average of these 3, and then a random number. You can use so many techniques you want, but the problem is the same. You have to start from somewhere because you don't have any clue about the data. Or you know some technique. Or you know some technique.
Do I know some technique? Yep. I only know one.
Which is?
I forgot. Silhouette.
What?
Silhouette.
Okay? And then again, it's hard coding, as we said. This is hard coding. You have 0 and 1. So the classical example in literature is something like this. You know, when we have maybe points like this, okay? So this is the butterfly problem, which is, okay, you have a cluster here, you have a cluster here, but this poor guy, where he goes? Nowhere. Okay? So again here, we flip the coin. Now we should be expert on K-mean. Okay? Thank you. See you tomorrow in the lab.